All right, today we are talking kinetic and potential energy, which we have learned before, but we are going to talk in it as a lens of like how do we calculate how much kinetic energy changes if we change speed and how much potential energy changes if we change height. So let's refresh kinetic energy. Earlier we defined kinetic energy as the energy of motion. The amount of kinetic energy an object has depends on both its mass and its speed. Here's our formula for kinetic energy. Remember, it is measured in joules. 1/2 mass velocity squared. So we've done this before. You practiced this before. You take 1/2 of the mass, you square the velocity, you multiply the two answers together. So just kind of having a refresh of how to do this. Here's kind of like what your units stand for. If you need to write these steps down to remember how to actually calculate it, that would be really helpful because remember the velocity is squared, not the whole answer. So kinetic energy, like all forms of energy, is measured in joules. This is the same unit of measurement as work, since the work is equivalent to how much energy is being transferred to something. So this equation implies that two objects with the same mass moving with the same velocity have the same amount of kinetic energy. Whether they're different objects or not, if they have the same mass, they're moving at the same speed, they have the same amount of kinetic energy. If two objects with the same mass are moving with different velocities, the object moving faster has more kinetic energy. And if two objects are moving with the same velocity but have different masses, then the more massive object has more kinetic energy. And you've seen all of this before. This is hopefully review to you. So here's a practice question. A rock is rolling at 12.5 meters per second down the hill. The rock's mass is 180 kilograms. What is the kinetic energy? Well, we take 1/2 the mass, which is 180, times 12.5 squared. We got half the mass is 90. 12.5 squared is 156.25. We multiply them together, and there's your answer. And I forgot to put the unit, but the unit is joules. Good. So gravitational potential energy, you've probably heard something along the lines of like you've got the potential to. The same goes for objects that are located some height above the ground. If allowed to fall, the force of gravity will do work to bring the object towards the center of the earth. They have the potential to fall and speed up as they get closer to earth. As we will see very soon, energy is conserved, so there must be a form of energy that is transferred to kinetic energy as the object falls and speeds up. We call this gravitational potential energy. We're going to use GPE for short. So the gravitational potential energy is measured in joules as well. It depends on the force of gravity and the height of the object. So the change in H represents the change in height. This can be positive going up or negative going down. So you could do this formula in a couple ways when we talk about changing the height of something. You can calculate and just subtract the heights, or you could calculate it twice, as I'm going to show you how to calculate it twice. Your gravity constant, remember, is always 9.8 meters per second per second. This is always, always, always the same. So when you see that G, it's always going to be 9.8. Mass is M, G is the force of gravity, H is the height, or you can have it be the change in height if you want to calculate it in that way. All of this is multiplication, so it's very, very, very simple. Why are there so many deltas? We see these like deltas here. Those are the triangles. The amount of gravitational potential energy is relative to a reference point. This could be the bottom of a ski hill, the Earth's surface, or a particular starting and ending point. When solving problems, set the lowest point as a reference where the GPE will equal 0. This will aid greatly when solving conservation of energy problems when we get to conservation of energy. Which point is the best point on the roller coaster to set the height to 0? So what I would do is I would look at the roller coaster and I would pick the lowest point on the roller coaster, and that would be our 0 point. So the best point here would be B. It's closest to the ground. That would be our 0 point. Here's an example of potential energy, gravitational potential energy. You have a 60 kilogram bungee jumper who is at the top of a bungee jump, 48 meters above the ground. Mass is 60, height is 48, gravity constant is 9.8. You just multiply them. 60 times 9.8 times 48 is 28,224 joules. So that's how you do just a normal gravitational potential energy if you're just calculating that. Let's talk about the change of things. So if we have something that is accelerating, we're back to kinetic energy. We have to calculate kinetic energy twice and then subtract. So if I'm asking you, your next question is, a cheetah is a mass of 72 kilograms, accelerates from 10 kilometers to 120. So we have to do a problem for both of those. We need to find the kinetic energy of the cheetah at the end and its fastest speed and the first initial speed that they give us, and then we subtract those answers. So you take kinetic energy number 2, so your final speed, minus kinetic energy 1, your initial speed. And this is just broken out, 1/2 mass velocity squared. So the second velocity minus 1/2 mass, the first velocity squared. So let's take a look at our cheetah. We have 72 kilograms, 110 kilometers per hour to 120 kilometers per hour. Determine the increase in kinetic energy. So our initial velocity, we're going to calculate for 10 kilometers. So the mass was 72, velocity is 10. I take 1/2 72 times 10 squared. And then we're going to calculate a second problem for the final velocity. So at 120 kilometers per hour, it's going to be the same thing. Mass is 72, velocity 2 is 120, 1/2 72 times 120 squared. These are your answers. So our initial velocity when the cheetah is going 10 kilometers per hour, the cheetah is going 3,600 joules of kinetic, has 3,600 joules of kinetic energy. And when the cheetah speeds up to 120 kilometers per hour, the cheetah is now, moving very, very fast and has a lot more energy. So now it has 518,400 joules of kinetic energy. So to find the change, we need to subtract these. We take the final minus the initial. So we take the final, which is 518,400, minus the initial, 3,600, and your total answer is the cheetah's change in energy was 514,800 joules. So from when it started to when it sped up, it changed in that much amount. We can do the same thing with gravitational potential energy. You could do this in one of two ways. You could just subtract the heights, or you could calculate out this twice. So, example, Mount Everest's peak is located 8,848 meters above sea level. Base camp is located at 5,364 meters above sea level. Sea level is 0. Determine the change in GPE from sea level to reach base camp. So sea level is our first height. Base camp is our second height. Sea level is 0, so that would be 0. And then base camp is our height 2. So I calculated these out. I'm assuming an average person is 70 kilograms, so I just use 70 as your mass. So 70 times 9.8 times 0 is 0. 70 times 9.8 times our second height, which is 5,364, that's base camp, equals 3,679,704. So at the end, I would subtract those two. I would take the 3 million number minus 0, and my answer is at 3,679,704 joules. That is your change in gravitational potential energy from sea level to base camp. Then it asks for a second problem, determine the change in gravitational potential energy to travel from base camp to the peak. So our starting height is now starting at base camp, and our ending is going to be at Mount Everest's peak. We're going to assume 70 kilograms again. So I'm going to just solve this twice. 70 times 9.8 times 5,364. That's base camp. That's the same number we just calculated, so I just copied that over. Then I'm going to do it for the peak of Mount Everest. So 70 times 9.8 times 8 8,848 equals 6 million, and some numbers. I take the final height, or the final gravitational potential energy, which is at the very top, minus the initial, which is base camp, and there is my change in potential energy for this problem. Another way I could do it is I could just subtract the height. So I could take 8,848 and subtract it from 5,000 and use that as my height, and just do one calculation. But since I already had the second calculation, or the first calculation, I already did it. Great. So now it's your turn. You have a bunch of should do practice problems. You should do these. The answers are going to be on the module in the should do portion of your module. You should do the question first and then check your answer. That's going to help you the best. If you have questions, let me know.